Okay, so this is just a continuation of the exponential stuff. Okay, this is really kind of what that first section in chapter 4 is about. Looks at exponential functions and maybe some applications of these functions. So what I was going to do is just show you two basic applications that hopefully you've seen in the past. The first one, well, let's look at this first of all. This is your basic exponential function, right? Where your base can be any base. We'll look at the graphs. I'll make another video to show you quickly how to graph these and the different transformations. The thing to notice is that the variable is in the exponent. That makes it an exponential function, okay? This is just the same thing as that. We've got ABX or BX. This just means that you have something to start with. We'll look at those in this section. We'll make a clarification between those two. The first thing I wanted to show you quickly was compound interest, okay? Now, we've seen simple interest in the past. Simple interest, right? And that is simply found by the principal times the rate times the time. I per is what we call that. The interest is equal to the principal, the starting amount, times the rate, which is your interest rate, and time, which is years. Now, that doesn't take into consideration the fact that when you're earning interest, then that money is now yours, so you're earning interest on your interest. And that's where compound interest comes into play, all right? And this is essentially the compound interest formula. Hopefully you've seen it in the past. If you haven't, well, here it is, okay? Where the A is what we want in the end. That's the final amount. So the original amount plus your interest. The P here, we call it the principal. It's also the initial amount, what you started with, okay? So what you put into your interest, into your bank account or into the term deposit. This is just a 1. I'll explain to you why that's a 1 there. Your R is your interest rate, and it's usually given per annum, interest rate per year, right? So if I have, say, 5% interest rate per annum, right, the decimal that we use is 0.05. That's what we use in our calculation. N is the number of compounding periods per year, so you can compound it yearly, which means that they take the interest at the end of the year and put it in your account. You can compound it monthly, which means that they take the interest every month and put it into your account. You can compound it daily, weekly, quarterly, biannually, semi-weekly, bi-monthly, tons of different ways that we can compound it. We'll hopefully clear up any of those issues as we come up. And then that's the number of compounding periods, that's the number of compounding periods, and then T is the time in years. So say, well, we'll go through these questions. Let's do one just to see if we can sort it out here, okay? So now, find the amount that you would have if you invested $6,500 at 4.5% for 5 years compounded. Oh, and we're going to do a couple different ones, yearly or monthly. So first of all, think about which one of these would have more money, right? Now, if you're compounding it more often, it means you're getting your interest more often, which means that you're earning more money quicker. So the more you compound it, the more you should actually have, okay? Now, let's identify the P value. The P is the principal, so it's going to be $6,500, and then it's going to be 1 plus 0.045 over 1 times 1 times 5. Now, give that a shot. See what you come up with on your calculator. The key to plugging these in is making sure that you do the right math on your calculator, right? So I'll slide this up again so you can see my calculator. And what I do is I often start in the middle. So 0.045, I don't have to divide it by 1, but I can just for future references. Then I add the 1, right? And then don't forget the order of operations that you put it to the power of 5 now. And then you multiply it by the original amount, and you end up with $8,100, okay? So $8,118. So now, let's look at the next one. Well, let's slide it down again so we can see all the definitions. The principal, the starting amount is $6,500. The 1 plus 0.045 over 12, because I have 12 compounding periods in a year. 12 compounding periods per year for 5 years. Okay, so that changes your exponent. It also changes your rate on the inside. Now, some of you might ask what the 1 is for. Well, the 1 includes the original amount. So boom, that gives me the $6,500, and then boom, that gives me the interest. If you didn't have the 1, all you'd have is the interest, okay? So now, the key would be to plug this in correctly on your calculator. Please give it a shot right now, and we'll see how you did. So what I do is I do this first. 0.05 divided by 12. Now that's the interest rate per month then. I'm going to add the 1 to the power of 12 times 5 is 60. Boom. And now I multiply it by my original amount. And you end up with a little bit more, which kind of makes sense. 8136 and 67 cents. So that is your basic compound interest formula. Okay? There are obviously a bunch of different types of ways that we can ask these compound interest questions, and here's another one. Looking for the initial investment is required to become a millionaire in 25 years if you have a term deposit at 12% compounded quarterly. Okay, so the trick is now to fill in the appropriate things. Now, do you have the final amount? I think we have the final amount. We want $1 million. So $1 million is equal to, I'm looking for my P, right? And then I have 1 plus, well, my interest rate is 12%, so I'm going to go 0.12. Quarterly means that my N is 4, right? So 4 times, and I want to make it in 25 years. So you can see that what we have here is simply a algebraic equation where we're looking for P. So if you wanted to find P, it essentially would be 1 million divided by this whole thing. Divided by 1 plus 0.12 over 4 all over, to the power of 100. So the idea here now would be to see if you can get this number on your calculator. All right, so let's see what I can do here. So I'm going to have 1 million. Actually, I'm going to do this. I'm going to do it like I did before. 0.12 divided by 4. Okay, plus the 1. Enter. And then to the power of 100. Oops, I did it wrong. It went times 100. So 0.12 divided by 4, right, plus 1 to the power of 100. Now, what I need to do is 1 million divided by that. So 6 zeros divided by that answer, and you get $52,000. $52,032.84 is what you would need to be a millionaire if you didn't touch that money for 25 years. Okay? Might seem like a lot, but 25 years is a long time, and 12% is a pretty big interest rate. So that's compound interest. Okay? What we're going to look at next is growth and decay formulas. You've looked at these before when you dealt with radioactive half-lives, or if you dealt with population growth. Okay, this is the first one. We got two different types we have here. Okay, where AO is your initial amount, X is your growth factor. So if it's a half-life, then it's a half, right? If your population is doubling, then your growth factor is 2. If it grows by 10%, then your growth factor is 1.1. Okay, so the growth factor is something that we're going to have to figure out. The T is a time elapsed, and the T is a time of growth or decay. So if you have a half-life of 50 years, your big T is 50 years. Okay, so let's see how we can apply these. Now, before we do that, I'm going to show you another one here. These are very, very similar, and they will give you very similar amounts. The difference is that this is used for continuous growth or decay. Okay, so that is any natural occurring growth or decay would pretty much follow this natural sort of growth, and that's why we use this value of E. E is a special constant called Euler's constant. It's just a constant that they figured out, okay, that applies for continuous growth, just like we have a gravitational constant, we have electrical constant, we have constants for a bunch of different calculations. Planck's constant, there's just a bunch of them, right? And Euler's constant is approximately 2.71828. So we're going to use, do a question here and use both of these formulas to see if we can find some answers. Okay, so now Half-life of plutonium is 239, is about 25,000 years. How much will remain after 2,000 years? So what you don't know is what you started with. So what they want to know is maybe a percent that's left, or what percent is left. So you're going to start with 100, okay? So how much you have is going to be 100. Well, a half-life means that your x here, right? Your x here is a half, right? And the time elapsed is 2,000 years over 25,000 years. So it's as simple as that, right? And what we're going to have to do is work that out on your calculator. So remember the order of operations. You have to do this first, right? So 0.5 to the power of, let's go 2,000 divided by 25,000, and you get this number here. Then you multiply it by 100, and you have 94.6% left. Okay? We don't actually have a way to solve this yet, because what we're going to have to do is find decay. So what we need to do, and what's happening with all of these functions, is that we are given the exponents, okay? Logarithms will allow us to find exponents when we don't have them. All right, so we're going to deal with this bad boy soon, okay? But right now, what we need to do is work on this one, okay? I got one more example here. The number of fruit flies here increases by 25% every 3 days. So that means that it's growing every 3 days, okay? So in this case, what would be your growth factor, right? Your growth factor is 25% more, but it has to be 1.25 because it's growing. If it was decreasing by 0.25, it would be 1 minus 0.25, which is at 0.75, right? So that means that your big T is 3 days. Okay, because that's how long it takes to grow. My amount, not my initial amount, right, but the amount I have now, after 25 days, well, let's do the little t first. So little t is 25 days, and the amount that I have at the end is 2,000. So what I'm looking for is the initial amount. Okay, so if we plug it into the formula, what we're going to end up with is I have 2,000. I don't know what I started with. I know my growth factor is 1.25, and it's little t over big T. Little t over big T. So that means that it's grown about 8 times, right? Because 3 goes into 25. Oops, you can't see that. Sorry, guys. Let me erase this so that you can see it a little bit better. It's 25 days have elapsed, and it takes 3 days to grow, right? So now it's a matter of plugging it in again. So this, your initial amount will be 2,000 over 1.25 to the power of 25 thirds. So let's do that. 1.25 to the power of 25 divided by 3, right? Boom. That's that. So now you go 2,000 divided by that number, and you get 311.5. So there's actually 311 to start. And that's how we find the initial value. Here's a couple, so there's a few examples of how we use exponents and exponential functions. We'll look at graphs next, and hopefully that helps.